In this video, we're going to talk about properties of continuous time Fourier transform. Now, in this video, we're going to take advantage of the fact that we have the table in front of us. Who not only we're going to look at Fourier transform for periodic signal, we're also going to look at it for aperiodic signal as well. And remember that the periodic signals also, the easier way potentially would be to take the Fourier transform of it, a Fourier series of it, and find the coefficient because that's discrete. But Fourier transform can do it. Then we use the delta function, the impulse function, to make it discrete. But we'll talk about it as we go through. The properties are really important because the properties table or properties in general allow us to look at the signal itself, x of t, and then predict what the Fourier transform properties of it may be, or vice versa. If somebody gives us a Fourier transform of a function, we can look at that and make some predictions about the attributes of our actual signal, which is very useful. That, in another word, we are able to look at the frequency domain of a signal and predict how the time domain looks like, what the time domain looks like, and we can look at the time domain and predict what the frequency domain looks like by just simply knowing what those property relationships are. Now, in this video, I'm not going to attempt to derive these properties. That is available on the text, and you're more than welcome to go back and look at it, and I encourage you to at least look at some of them to get a flavor of how the proof is done. But because otherwise this video would be way too long for watching, so I have to make it into a mini series. But for now, though, I just want to make sure you understand this video goes through the key properties and how they impact us. So let's go down the list on this one. For example, the very first one, as you look at the very first one, it basically says if x of t is real, then x of j omega is going to be a conjugate of x of j minus omega. If you recall, that's kind of akin to a of k being equal to a minus k conjugated. And again, the reverse of that is true. If you look at the next line, it's literally more or less not the reverse of it, but it says if I know the transfer function for x of t is x of j omega, then for x conjugated t is x of minus j omega. Now, here's a biggie, and I'm going to use the red thing to outline this one, and we'll talk about what this is called. Convolution. And this is a pretty big property from our point of view. Why? Because let me go down here and do that. So first, let's take a look at it. It says basically if I have a convolution in time domain, what do I get? I get a multiplication in frequency domain. That's a pretty big deal because remember how when you've done convolution, it's a pretty difficult process because you got to find the intervals and then do the integral and all of that kind of stuff. But here it says if it's a convolution in time domain, it's a multiplication in frequency. Awesome. So what's the implication for us? The implication for us is if I've got a system and my system has an impulse response of t, we know that if I put an input of x of t and I get a y of t out of here, then my y of t would be a convolution of x of t with h of t. And if you remember, that is a whole integral that goes like integral from minus infinity to infinity of x of tau, h of tau, h of little h of t minus tau, d tau, and all of that. And you have to go through and figure that out. Now the beauty is that if I were to take this and find a Fourier transform of the impulse, it's called the transfer function. This was the impulse function. The name for this is impulse function. And as you recall, the name for this, oh, by the way, they write it as h of s, or if you like, you can write this. This is basically j omega for in the case of a Fourier. So this would be basically a Fourier transform of h of t. Pretty cool. So if you look at this and say, okay, I'm going to take a Fourier transform of this, and I'm going to call it x of s or x of j omega. Either way is fine. And now you got to get comfortable to seeing it both ways. And if this is x of, actually let me write it as x of j omega, because I think we've been using j omega so far. So, but know that s is a shorthand for j omega for the case of Fourier series. So x of j omega, which is going to be the Fourier transform of x of t, and again y of t, take a Fourier transform of that, and that would be y of j omega. It would be the Fourier transform, right? But then, since this is a convolution of x of t and h of t, y of j omega simply would be the multiplication of x of j omega and h of j omega. That's pretty cool. So if I have h of j omega and x of j omega, I just multiply them and then I know what my output is. And in many times it's easier, especially with computers, but even manually, to take our x of t, h of t, y of t to the frequency domain, find their Fourier transform, manipulate it, find y of t, and convert it back to time domain. Okay, so that's so now if I haven't got the message yet, that's a pretty big deal for us. Some of the other things that are interesting, but I'm not going to spend as much time, but they're not as equally important, but they're still important, is like the derivation in one domain turns out to be a multiplication by a variable in the other domain. For example, in time domain, if I have a derivative of x of t, in the other domain, it would be s or j omega times x of j omega. I can shift in one domain. It allows the other domain to be multiplied by e to the j omega. And the integral, you can go back from integral is a division. You have some constants you have to deal with. If I have two functions and I add them in time domain, their Fourier transform would be Fourier transform of each one added together. And okay, all is fair because convolution in time domain, when it became a multiplication in frequency domain, the reverse is also true. A convolution in frequency domain is a multiplication in time domain. And some of the symmetry questions like real, odd, how did they impact x of j omega? And then, and we can, for example, frequency shift can be translated also. As you can see, we are multiplying the time by b, which means we are either shrinking or increasing our frequencies, time scale, so that we can translate time reversal, x of minus t. We can do time shifting from one to the other. And then, this one, even though we don't directly do much with it in this video, and next videos, but this is a really important concept. This is called the Parcel Relationship, and simply says that total energy in time domain is exactly the same as total energy in frequency domain. It kind of makes sense, but it's a pretty important equation too. It basically tells us if it's the same signal, it doesn't matter whether you're looking at it in the frequency domain or you're looking at a time domain, the energy is going to be exactly the same. All right, so that's the first use of this table is predicting what frequency domain is doing based on time domain and vice versa. The other piece was that really important to us is the fact that convolution in one domain becomes a multiplication. That means if I'm analyzing a system, all I have to do to find an output of a system is multiply x of j omega by h of j omega, and I'll get my y of j omega, which is the output. That's pretty cool. Now that's not it. This whole thing can be used for taking Fourier transform as well. The property can help us in certain cases to do that, but in order for us to do that, we have to take two tables in conjunction with each other. And this other table is available now. Is nothing really exciting other than the fact that some of the most common Fourier transforms have already been done in a table form, so you don't have to do it. You can look it up. Save some time. So as you can see, this table also has the Fourier series, because if you look up here, from here to here, these signals are all periodic. E to the j omega 0 is periodic, cosine is periodic, sine is periodic, 1 is periodic. The square wave, this is a periodic square wave. The pulse train is a periodic. So in these cases, not only you have a Fourier transform, you also have a Fourier series coefficient for them. Remember, So what this is basically writing the Fourier series as a function, but still this is a discrete function, right? As k increases, so you basically have a of 0 at omega equal to 0, a1 is at omega equal to omega 0, a2 is at omega equal to 2 omega. This is a kind of a way of writing a of k equal to that. Okay, so that's nothing exciting. So, but if you want to keep everything in Fourier transform, and they do pretty much in practice, I mean, most people don't go to Fourier series once they have a, and these days we have computer systems, so once we know how to calculate the Fourier transform, we just pump the function into Fourier transform and let it come out the way it's gonna do. And so in the case of a periodic signal, it resolves into, you'll have a fair amount of impulse functions used to make sure the function is discrete. And then these are not periodic, and they only have a Fourier transform. They will not have a Fourier series, because Fourier series only exists if the signal is periodic. And it gives you some of the common ones, you know, that we run into, for example, delta t, u of t, and that kind of stuff. Okay, so let's go back and take a look at some examples of finding Fourier transform. So one of the simplest ones would be, let's say somebody comes up to you and says, I've got a x of t, so that would be example 1. And these are all these problems are to find Fourier transform of something, of x of t. So if I have x of t and my x of t, I'm going to change color to black, is a little easier to see, I assume. X of t, then x of t, let's say, is equal to 5u of t. That's really easy, because I look up here in my table and it says, oh, u of t is simply 1 over j omega, right? All I'm going to do is look over here. So this says, okay, if you want a Fourier transform of x of t, right, that's x of j omega. I'm just going to look up at the table, and the table tells me that u of t is, the 5 is just a coefficient, is 1 over j omega plus pi delta omega. Perfect. I'm done. That's the Fourier transform of that. We're good to go. Now, life might get a little more complicated, so you might have a case. This is case 2. X of t is not as simple as we had it there. X of t may look like, let's not get too fancy. Let's say is 9u of t minus 5. And you look in your trusty table and you don't find u of t minus anything in here. It's just u of t that they've given you with this equation. So now what do I do? And then you go back to your properties table. You take a look at property table and say, oh, one of the property tells me that x of t minus t0 can be whatever was for x of t, which didn't have the minus t0, but I have to multiply it by e to the j omega t0. So in here, I come in here and say, oh, t0 is equal to 5 for this one. That means all I have to do to make this work is take this and multiply it by e to the j omega 5. As you see, this is what I'm doing. I'm taking advantage of this property right here. Okay, so in this case, I just say no problem, and so all I do, was it a t? I forgot. Let's take a look. The t0, yeah. So that's all I do. There's no t here, and then basically pull in what was without the shift in here. So it would be 1 over j omega plus pi delta omega. I think close. Actually, let's make it a square bracket. It's a little easier. Okay, so that's the answer to our x of j omega for this x. Okay. Now there is another. So far what we've done is, well, it's really simple. I look at the table of given Fourier transform and I have the answer. I'm done. The other one is I look at the table. I don't see it exactly, but when I look at the property, I see a way of converting it, and that's good. Now let's say somebody gives you another x of t, and the x of t, this might be easier if I give it to you in graphs, but it could be given to you in equation as well, not a big deal. And so let's say they give you an graph that looks kind of like this. This is t. This is the magnitude. Let's make it a little more interesting, so maybe make this one a little bigger. So let's say this is set at 10, magnitude of 10. This is magnitude, pulses magnitude of 5. And by the way, these are all 0. I drew it a little bit above the line just so you can see it. And this change is happening at, let's say, 1. This change is happening at 3. This change is happening at 4, 5. Let's say this is 6, maybe 7. And then it's 0 all the way out here, and it's 0 all the way there. So they give you x of t like this, and they say, okay, find me the Fourier transform of it. You go over here and say, hey, I can't find anything that already have the Fourier transform, and there's no property I can use to convert this to what I have, so I'm stuck. At this point, the only choice you have is to really use your x of j omega equation and try to work through the process of finding the x of j omega through the Fourier transform integral. At this point, you got to do the heavy lifting yourself. There's no quick key to answer, so you go back and say, okay, x of j omega, I know that x of j omega is integral from minus infinity to infinity of x of t e to the minus j omega t dt. To take a Fourier transform of, in other words, this is a Fourier transform of x of t. Okay, so that's pretty, not easy, but we can it's not too bad. We can do it. So you look at this thing where it's 0, you don't have to worry about it. That means your integral will get reduced to integral from 1 to 3, 10 e to the minus j omega t dt, plus integral of 4 to 7, 5 e to the minus j omega t dt, and once you take care of that, you get your answer. Okay, we're not going to do that in the video because we're confident you're able to do it. That brings us to the end of this discussion of how to use the property table and the standard relationship, the standard Fourier transform that usually are available on a table format to figure out what it is. So this is just a common transforms that are available to you. This is the properties tables that's available to you. So if somebody gives you an x of t and say what to do, the first thing you want to do, you want to see, can I just use the table and get it to give you the answer? If it's not, can I use the properties table to make it look like one of the common integrals, common Fourier transforms, so I can give you the answer? And if it doesn't look like, as a last resort, you go and actually work on the Fourier transform integral. You actually write the Fourier transform integral, work it through, resolve it, evaluate those integrals, and get the answer. All right. So that brings us to the end of this video.